right, here we go, talking about PASCO's certified version of OpenSciEd biology, chemistry, and physics. And we're very thankful that you have joined us today. We appreciate you being here. And we're going to cover how PASCO has treated the curriculum and infused our sensors and technology into it while retaining the program itself. Understand that this program, every single unit in it has gone through a third-party review conducted by the nextgen.org, and you can find equip rubrics that show the capacity and strength of these programs directly through the nextgen.org website if you wish. Understand that all the resources we're going to show you today come in editable versions, so schools, districts, teachers can adjust curriculum that fits best for them and their students. And through the program, one of the huge things here is the hands-on component, where students are investigating real-world phenomena, not just through reading and writing, but also through conducting hands-on experience, collecting real-time data, and formulating their understanding of that phenomenon through the course of the program. The PASCO certified versions do follow the support of the next generation science standards. So you can see how those are outlaid here. They also connect through cross-cutting concepts, meaning that skills that work in physics will also work in chemistry and biology. So you'll see arrows that connect from content to content, and that's what it's representing. You're also going to be exposed to engineering design activities, so the science and engineering practices are also heavily supported throughout this curriculum. All right, so why choose PASCO? PASCO's been around for over 60 years. We are well known for our sensors and our software. We support K through university classrooms, and we're really excited to be part of this program. So with us, you're going to be able to see some of the things we did today, including videos. You're going to see 3 videos today that show activities in action for biology, chemistry, and physics. So you have a good idea of what we do, and you'll have the recording later to share if you would like to let other folks know. And with our equipment being so durable and so well known, there are other vendors that are actually putting our sensors into their kits for OpenSciEd. So that lets you know too just how special our products are. All right. So one of the things PASCO did, we released recently our PASCO portal. And the PASCO portal is different from our website, as we've made sure to streamline resources and organize them in a certain way. So everything in there is up to date. You can have everything at a touch of a button, and the organization is key with OpenSciEd because there's a lot of documents. You have unit overviews, you have teacher editions, student editions, simulations, videos, and more. So what the portal will do is we separate each one by content areas. So you'll be able to select 6th, 7th, and 8th grade if you went the middle school route, and then you can have access to biology, chemistry, and physics if you go that route. And we go by starting with the units as a whole. So we'll show you the unit overview and all the documents that go with it. And then underneath each unit, you're going to see all the lessons that go with that unit. And I'll show you a resource later so you can see a little bit more how the portal works with the OpenSciEd curriculum, but it's just something I wanted to point out up front. Another interesting thing in terms of using our portal and going with OpenSciEd, our version of the curriculum, is it's a school site license. So if a school wants the grades 6 through 8 curriculum, they can go that route, which means that the majority of the teachers in that school will have access to all levels of programs. So if you have a 6th grade teacher that wants to pull in something from 8th grade, they have access to those resources. The same goes for biology, chemistry, and physics. So if a school gets the site license for the portal and access to the OpenSciEd curriculum, your chemistry teachers will be able to view physics and vice versa. And this really helps when you have teachers that are in multiple prep areas. All right, and you can see the breakdown here on how we work the files. So the portal gives your district and your schools connections to your learning management systems, such as Canvas and Blackboard, and it gives you, the teacher, the ability to push student resources using that learning tool and operability to send them directly to your learning management system where you can do additional ordering and adjusting as you see fit for your program. The equipment kits. So yes, we have infused many of the activities found in high school with our sensors and our software. And along with being a certified kit provider with OpenSciEd, giving you consumables and non-consumables with that support, we also provide equipment packages with the PASCO equipment. So you can do those real-time data analysis activities with your students and get that interest from the students raised up. They love technology, they want to use it. Some of us are afraid of it, but I guarantee you the students are not, and they'll take it and they'll run with it quite quickly. An important thing to point out is that the integrity of the original OpenSciEd program is held. PASCO has just infused activities and things that support the content that is already there. So storylines, the phenomena-based points, all of those things remain intact. PASCO, again, has just added some of our activities to that. So when we add PASCO materials, it doesn't just mean a sensor. So there are activities that are in the original version that require a good amount of DIY. It's things that teachers might have around the classroom. But perhaps you don't have the time to create 6 of these box assemblies for your students and groups. PASCO has taken a step and actually created a box that mimics the same activity that's in a one compact system. So you're not going to lose these parts, that you're not going to have to store a lot because everything fits in that box and then you can store it away when it's done. We've also changed it up. So you see on the left, there's a system here that's in the original where they're utilizing a brick and a force sensor, and they're measuring the force of impact of that cart onto the brick by using the spring scale and putting one of those ties around it, and that moves on impact. Well, we have the smart cart. Smart cart measures force, velocity, many, many different measurements. And we've included that smart cart with our pass track so you can conduct the same experiments, but now you're going to get real-time data in graphs that students can analyze and dig in deeper into the coursework that they're going to have to do and show how they understand the concept being presented. All right, so it is a rigorous curriculum. It does not only just cover the basic chemistry, physics, and biology standards. Understand that it's also infused with earth and space science standards. So that's covered throughout all 3 programs as well. Again, content organization, and I'll share with you in the end how you can learn more about this and actually have access to see it yourself. You can sign up for portal information by going to pascoportal.com. Actually, it might be portal.pasco.com, and you can get more information there. Our either Jonathan or Roger will put that in, or excuse me, either Jonathan or Isaac will put that into the chat, so you have access if you want to learn more about that, including the onboarding resources and many other things that you can access through the portal. All right, so let's dig into it. We're talking about high school, and you want to see what PASCO has done. So on the left-hand side here, on the OER version, students are learning about the phenomena of zombie fires and essentially how these fires will stay essentially burning underground in areas like the Arctic tundra. And when it gets warmer and drier out, they can flare back up. And so it's important to understand how peat plays a role in this and how temperature plays a role. So students with the OER version will be using different temperatures of liquid, and they will be dropping in Alka-Seltzer to see reactions. And what they're measuring here is the height of the foam using a ruler. So PASCO kept the integrity of that activity and have included our CO2 sensor. So now students are going to be getting a 250 milliliter bottle and the sensor in different temperatures of water and seeing the reaction that occurs with a sugar solution and yeast. So I'm going to stop talking about it and I'm going to let you watch a video that demonstrates the activity right now. And again, this is for biology. In this unit, students are exploring the question of what causes fires in an ecosystem to burn and how should we manage them. In Lesson 3, Decomposition Investigation, students explore how decomposition is involved in the flow of matter and energy in a zombie fire system. A zombie fire starts when a surface fire burns deep into organic layers like peat soil. This allows it to smolder underground and continue burning even though the flames above ground appear to be extinguished. This smoldering fire can then reignite and flare up again when temperatures rise and dry weather returns, essentially coming back to life like a zombie. Students will carry out an investigation using yeast and a sugar solution as they model to generate evidence to discover that temperature affects the rate of decomposition of peat and permafrost. This activity helps to answer the lesson level question of, why is there so much peat that has not decomposed in the Arctic? This investigation follows a student-led decomposition investigation planning activity, where students are presented with materials that will be used in the activity, and they identify independent and dependent variables. They also explore that when yeast is added to a sugar solution, bubbles form and indicate that it has been activated and is consuming the sugar. Students also have previously learned about peat and zombie fires and why they burn so much. Now in Lesson 3, students will investigate whether temperature affects the rate of decomposition of peat and permafrost using a sugar solution and yeast as the model. As you can see, the setup is fairly easy. Each group is going to get a wireless temperature sensor, a wireless CO2 sensor, a 250 milliliter sample bottle with 100 milliliters of sugar solution in it, a 500 milliliter beaker with 250 milliliters of either cold, warm, or room temperature water. These will act as individual water baths for the investigation. Students are also going to receive 0.7 grams of yeast that will be our model decomposer that we're going to be placing into the sugar solution. So you'll see that I have all three scenarios in front of me, so I can model each group's experience one at a time. In the actual activity, each student group would only be conducting one using one of the water temperature baths. And I want to note that these have already been sitting in these water baths for about 5 minutes before the students would begin. All right, now let's see what the students will be experiencing. The students will receive investigation handout. You can see decomposition investigation data and sense making. It's going to list all the materials that they're going to need to conduct the investigation. And then, of course, give the investigation question of how does temperature affect the flow of matter and energy from sugar to carbon dioxide by decomposers in a zombie fire system. Step-by-step directions are included, along with images to help them with their setups. And then after they go through the activity, they're then going to fill in their data table based on the SparkView data that they collected, and they're going to be collecting points every minute. And that'll make sense when we dig a little bit more into the SparkView file. All right, so I'm going to get my goggles on. And I've already opened the SparkView file that the students would be using, labeled B.2, Lesson 3, Decomposition Investigation. So PASCO has created such files for many of the experiments utilizing our software and sensors. So students can get started quickly and focus more on the data collection rather than the setup of the software. Once I open the file, I'll need to connect my CO2 sensor via the Bluetooth icon. I'm going to choose that up here. I'm going to turn on my CO2 sensor. Bluetooth is blinking red, letting me know it's ready to connect. And then I can also match the numbers on my sensor 352 to the ones I'm seeing on the screen, so I ensure that I'm connecting the proper sensor. All right, while that's connecting, I want to point out that students are going to get the wireless temperature sensor, and it has the LED screen, the digital screen here. So We can connect this to the software if we wanted to collect temperature data, but for this investigation, they're simply going to use it to see the temperature of their water bath. And this becomes particularly important when they're using the warm water bath, because we want to make sure that the temperature in here doesn't exceed 43 degrees Celsius, because that's when we can kill off the yeast. Okay. All right, so let's start our data collection. And again, my sensor's set up. The SparkView file is set to run for only 5 minutes of data collection, and it'll stop because we know sometimes students don't hit it right on that mark. This way, every group has exactly 5 minutes of data. All right, so I'm going to start with my cold water bath over here. And again, I've got the sample bottle in the ice water bath. It's been in here for about 5 minutes. And then I'm going to add my decomposer, my yeast, into the sample bottle. And you can kind of stir it around or use a stirring rod to get this fairly dissolved before you begin collecting data. Okay. All right, I'm going to quickly insert the CO2 sensor, make sure it's snug in that bottle, and then I'm going to start collecting data. And we'll speed through the data process. That way we can show you all 3 scenarios. Okay, so our 5 minutes are up. We have our first run. And what I'm going to do is scale to fit my graph just to have a cleaner sense of the data. And now all we need to do is remove the CO2 sensor. Remember, again, students would only be conducting one of these, but we're going to do all 3 so you can see how they work. Now I'm moving to the room temperature water, and I am going to add my 0.7 grams of yeast, my decomposer, into my sugar solution, and give it another stir. Okay, place it back in. And I'm going to put the sensor back in snugly into that bottle and start data collection again. All right, so our second run is up with the room temperature water. Now we got 1 more to go with the warm water. I'm going to take this again out of the bottle. Put my yeast into the sugar solution. Give it a bit of a stir to dissolve. Okay. Get the CO2 sensor in there, and then start data collection for our final run. All right, so another 5 minutes is up. We have collected our data for the warm water. I'm just going to take my CO2 sensor out of the bottle for now and set it aside, and bring you over to the software to show you how students would experience the software. So I'm going to go ahead and start by showing my first run. It has been scaled to fit my graph. And one of the things the students can do is rename the run. So if they were the group that started with the cold water, which we have here, we can go in and we can actually rename that run. I can just go to 1, and I can rename that to cold water. I can then, I'm just going to model it for you now. Run 2 was with room temperature water. And then our third run was with warm water. Okay, close that. And now you can see each run is named by the temperature that I utilize. So this is great if a student has to come back the next day to do data analysis. It's there for them, or they can share the file with other students. Okay, so the students are asked to collect a data point at every minute. So one of the ways they can analyze the data and get those numbers is they can select right at the 1 minute mark and then use the coordinates tool to mark that CO2 reading in parts per million at that point. Then they can do the same for 2, 3, 4, and so on. All right, I'm going to go ahead and show you all 3 at once, and then scale to fit. So we can definitely see a trend here, and this is what's so powerful about the software. So once the students have all this data collected, they're going to end the activity by finding other groups that use different water temperatures than theirs, and they're going to fill out the data table, which you can see here on the student sheet, and then make a graph using that data. I do want to point out that we do provide answer keys, of course, to the teacher for each of these, and along with the answer key, just like we provided a SparkView file for the students, we also give a sample data file for the teachers as well, so they can see how the results should look. Once students collect, share, and then analyze data, they are able to use evidence to support the claim that in a permafrost peat system, cold temperatures slow the rate of decomposition. Additionally, students discover through hands-on investigations and readings of scientists that peatlands act as a carbon sink and that rising temperatures can disrupt this function by causing increased carbon releases from the decomposing peat, which contributes to the phenomena of zombie fires. Thank you for joining the PASCO OpenSciEd student experience. All right, so now we're going to move on into the next activity, which is going to be chemistry. And here students are learning about the lightning phenomena and how that can occur with water connections. And they're looking into a salinity experiment. And you'll see on the left, you have the OER version where they have various pieces, some that are similar to what PASCO has created. But PASCO now has introduced our wireless current sensor in there to collect real-time data. And now Barbara is going to demonstrate this activity for you now.
In the saltwater conductivity investigation, students explore lightning safety as it relates to water. Students will figure out how increasing the concentration of salt in water affects the rate of charges flowing through it, then relate how the dissolved salt found in different water sources like oceans, lakes, and swimming pools allow those water sources to conduct electricity. Evidence gathered from this investigation helps students evaluate a claim that a lightning strike on a river caused the death of a group of geese floating on it. This investigation follows a teacher demonstration where solid salt and distilled water are tested with a wireless current sensor and light bulb circuit to see if those substances can conduct electricity on their own and when combined into a solution. The demonstration helps students understand how charge flows in the circuit and how to use the current measurement to calculate the rate of charge flowing in a solution that contains dissolved salt particles. Student groups then use the salt investigation plan handout to set up their own investigation and decide what percentage salt solutions they will test, given 600 milliliters of distilled water and 50 grams of salt. The student-determined solutions are to be tested according to the salt testing procedure, which I am now going to run through. I have 6 solutions prepared here, but student groups will have only one beaker in their setup and will have to mix and test solutions one at a time. I chose to make 0.5%, 2%, 3.5%, 5%, 6.5%, and 8% salt solutions. There's no need for a control, as students have already seen that pure distilled water does not conduct electricity in that demonstration. Remember to fully charge the wireless current sensors and share the water conductivity SparkView file with students ahead of time. Students will open the water conductivity SparkView file, turn on the sensor, and connect it. Use the menu at the bottom left to zero the sensor. Then start data collection. Leave SparkView running until all the measurements are done. Set the electrodes in their separate beaker zones so they don't touch. Now record observations of light brightness and current reading in the table on the salt investigation plan handout. I can see that the bulb is very dim, but it is on, and my current is reading about 99 milliamps. Students will have filled out columns A through C, as seen here, during the investigation planning. Students will test solutions from lowest to highest concentration. The procedure reminds students to rinse their equipment between testing solutions. Back to the zones. And as we test from lower to higher concentrations, we can see the current increases and the light glows brighter. Students will test all the solutions, but I'm going to stop here. Once all the current measurements are complete, stop collecting data in SparkView. Students will use a proportion of 1 milliamp of current to 6.24 times 10 to the 15 charges per second to calculate the rate of charges flowing through each salt solution. So there's that proportionality. Multiply the recorded current. So that first run was 99 milliamps to get 6.2 times 10 to the 17th charges per second flowing through this first beaker. Using the information in a Geese lightning strike reading, plus the quantitative and qualitative data from the demonstration and this investigation, students can now make an argument that either supports or refutes the claim that a whole group of geese in a freshwater system can receive enough charge to be electrocuted via lightning strike. The answer key includes sample student responses, plus the results for a different set of 6 solution percentages. Thanks for watching.
All right, so that was our chemistry demonstration, and you're probably hearing a theme when we talk about provided SparkView files, such as the sample data files and the student files. We did that for a reason. A lot of these setups are very easy if a teacher or student had to open SparkView and set up, say, tables and a line graph. But to save time, we made sure to create these SparkView files so a teacher could just send that file to the student and they can open it and it's ready to go, especially if there's set start and stop times, along with the various graphs and data analysis tools you're going to need to utilize for that experiment. So those are included with the majority of our PASCO activities that utilize the software. The last one we're going to demonstrate today is physics. I know a lot of you probably been waiting for that. So in the OER version, they are essentially creating a DIY coil and placing in those magnets, and they're creating their own generator. So they're going to be taking that device and they're going to be rubbing it between their hands. PASCO actually used our modular circuit sets, which we've already had, but then also created a new product, a hand crank generator. So students could do the same activity utilizing our products and again being able to see that real-time data in action and apply it to their understanding. All right, so let's watch the physics version.
In the first high school physics unit, Energy Flow from Earth's Systems, students delve into energy transfer through the context of electrical systems. Throughout the unit, students seek to answer the question, how can we design more reliable systems to meet our community's energy needs? In Lesson 5, Build a Generator Investigation, students test design features to see how they can improve the energy output of their generator. Prior to the investigation, students draw conclusions from diagrams of power plants and make connections between matter and energy transfer through fields. Students will explore 4 key design features of generators to respond to the lesson question, where does electrical energy come from? This investigation follows a discussion and modeling task on how power plants generate electrical energy. After students identify that spinning generators play an important role, they dissect a small generator to form ideas on critical components necessary for its function. Students will then explore each of these components during their investigation and evaluate different designs based on class-defined criteria for success. We'll focus on one possible criterion, LED brightness. Previous lessons have already covered circuit construction to turn on devices such as lights using PASCO modular circuits. Here we see a circuit made with modular circuit connector modules, 2 LED light modules, and a coil module. The modular circuits generator fits next to the wire coil such that the magnets rotate close to the coil without touching. We're using a 1000 turn coil, and all the magnets are oriented so that the north side is facing out to investigate magnet arrangement, as shown here in the handout. I can spin the magnets and see the lights are not turning on. Next, we can turn the magnets so that they alternate between north and south, as I've already prepared here. Now when we turn the crank, the lights do turn on. Students will test out additional magnet arrangements to better design an effective generator. Students next test the rotation speed of the crank. By spinning it faster, the LEDs light up brighter and more consistently. Once students have established that north-south orientations and greater spin speeds are more successful, they can test more complex ideas. We'll now see how it works with a different number of magnets, such as 4 magnets with north facing out. If I spin it fast enough, I'll light up even with only 4 north magnets facing out. Students will continue varying the number and orientations of magnets before continuing to the next challenge, swapping out the coils to change the number of turns. Here, we're doubling the number of turns by switching from a 1000 turn to a 2000 turn coil. Now the LEDs are much brighter. Students will try multiple other configurations as their time and ingenuity allows to determine the most successful design. After the investigation, students discuss their findings to come to a consensus on the factors that affect the energy output of the generator. To finish out the lesson, students will experiment with the modular circuits generator using compasses to better understand magnetic fields. Equipped with the knowledge from this lesson, students will continue to construct their model of energy transfer and energy flow from Earth systems. Thanks for watching.
So now you've seen a representation of all high school courses that PASCO has been working with and getting certified. We are, again, a certified vendor with OpenSciEd, and all of our activities have gone through rigorous reviews with OpenSciEd to make sure we're holding the integrity of the program. So we've talked about why PASCO. So you've seen 3 great reasons why PASCO, how the equipment can enhance the experience for students, maybe save some time on DIY for the teacher. There's other things that are of huge benefit. It's the PASCO portal. It's a way for you to push these resources directly to your students via their learning management system. We also have connectivity with single sign-on for ClassLink and Clever. Now, not only do you get the organization and access to the OpenSciEd PASCO resources, you get much more, because the portal includes much more than that. You'll have access to all of our most recent activities that have been uploaded in there for various sensors. So if you have a sensor that you're utilizing in an OpenSciEd activity, you can then look and see if there's other things you might want to do to add to your program or to build some more knowledge for your students utilizing that activity. You're going to have access to all versions of the high school curriculum. Again, chemistry teachers can access the physics and vice versa, and biology can access chemistry. That's a great advantage. We have a 5-year warranty on the majority of our products that are included in these kits. We also have a professional learning area within the portal. And what's great there is we include tutorials, which I'll share you links to two here shortly that might benefit you learning more information about the portal and the program. We also have certificate awarded courses that are on demand, asynchronous, the teacher can do on their own time. So, what PASCO is going to be providing in terms of professional learning right now, what we have scheduled so far is during back to school this year with implementation time, we are going to conduct a series of grade level content specific webinars. So we'll show you 6th, 7th, 8th chem, bio, and physics, and we'll begin with showing folks how to navigate the resources that's specific to their grade level and content, how they can push things out, all of the benefits of that, how you can view resources in the player, and what are the differences between simulations and video access and the additional pieces that PASCO has included in the program. So those will be offered. We're working on the times and dates. You will be able to register those later in spring through our pasco.com site under the training. So it outlines a little bit more in detail here what you're actually going to get when you join those webinars. So I talked about the asynchronous courses that are developed. We have an OpenSciEd PASCO certificate for the middle school, but we also have one for high school. So teachers can go through this at their own pace. We talk to everybody as a whole because understanding how to navigate the portal and the resources, that's good for everybody. And then also in that course, they're going to be able to view an activity from bio, chem, and physics, kind of like you did today, but it's going to be an authentic practice where the teachers will have the equipment there and they can actually run through the activities themselves to build that capacity. If you would like more information, Jonathan or Roger will put into the comments here the links to 2 tutorials. They live both on the PASCO site and in the portal site, but you can get them here. And the first one is a walkthrough of how the resources are organized and how you can utilize them. And the second video goes a little bit more in depth and actually shows you activities. Now, this one right now is for middle school. Today, we just covered the high school. So you have 3 videos to reference to see the PASCO difference in the program. If you want additional information, we also have recorded webinars that we have done previously. The links will also be shared with you. One is just talking about the portal itself and giving you a virtual tour of all the aspects of it, from support to how you can store products for easy access, access experiments to utilize other things, that training, and also the suite of software that we offer that will be available to you as well through the portal, including our SparkView software that you've seen today. We also have a webinar that might interest you where we have Matt Crable, who is the Director of Strategy and Growth with OpenSciEd, and he joined us to discuss the partnership between PASCO and OpenSciEd and the process we went through and the history of OpenSciEd and its creation and why finding curriculum that supports the NGSS national standards was so important. All right, if you would like to reach out to find your sales consultant, you can go to pasco.com and the support center where you can submit a consultation request form and you'll get connected with the correct person in your region, and they can work with you and assist you as you see fit and as needs come up. So I want to thank everybody that joined today. I am going to go ahead and stop recording. And after that, please feel free to stay on. We can answer more questions in the chat and get you the answers that you need. So stopping the recording, but please stay on if you would like to talk.